an interesting project presentation, especially a very great title here, a revolution that you must be part of it on a computer-aided mixed design. But before that, let me say a few words about the background of Professor Limbing Wang. Again, as a professor at Virginia Tech, he's also an adjunct professor at the National Center for Materials Service Safety of China. This is a new center, as I understand, they're establishing in Beijing now. And as with Limbing's specialty here has been already very instrumental in getting the Payment Mechanics Committee with ASC Engineering Mechanics. So he's been the founding chair of the Mechanics of Payments Committee and the vice chair of currently the Nanomechanics and Micromechanics Committee of the Engineering Mechanics Institute. So Professor Wang has led over 55 research projects funded by all the national, federal, as well as state agencies. His research areas, especially important here for us, paving materials and sensing and renewable energy technology. So I know he's done a lot of work on some of the multi-scale characterization, modeling, simulation work. But the most interesting is that recently Dr. Wang's research has integrated some of the modeling and simulation with experimental measurements. He has established a multi-scale characterization lab with equipment including an AFM, micro-CT, and a nano-CT, laser scanners, optical microscopes. On some imaging work, again, I worked with them over the years. So I'm hoping that all of these new devices and the technologies will be coming into the computer-aided mixed design. You'll be fascinating us with this talk now. So, Professor Wang.
Thank you, Aaron, for the nice words. And it's really a great pleasure, for my former classmate, and also close friend, Al, to introduce me. And we worked, on a number of initiatives, projects together, and close friend. And yesterday we chatted about the history, talk about how he drove that, big, car in there. And it's really a great honor for my close friend, and I talk to him as a mentor, as my mentor. Although we are similar age, but by career-wise, Ima truly is my mentor. Right now in Virginia Tech, I'm sitting, in his office, his phone number. Somebody, still called me. May I speak to Professor Ima Kadi? I said, well, he is in Illinois right now. It's been so many years, and truly, it's enjoying the friendship and also working together with Ima and Aaron, and also Jeff and Ouyang, so many good friends over here. Under the leadership, I think Ima really sees a tremendous of big kind of progress in this group as well in the past maybe 10 years or two. And also the entire nation, there are some kind of islands here together, and then we can work under that kind of flagship in there to promote our community, pavement materials, and to that other community like structural engineering, material science, to recognize that what we are doing over here is nothing less scientific, and we are doing a lot of great jobs and meeting a lot of challenges as well. And that's the work that we work together for many areas, and I will share with you on this relatively kind of new area. It's material design. Although actually it says new area, but it's been working on this area for many years since I started as my PhD program in Georgia Tech. My dissertation is on the microstructure and micromechanics of asphalt concrete. And from then on, my entire career, I always devote a part of my research on this area, computer-aided mixed design. Right? What I'm doing actually unconsciously, very beginning, I don't see that this is something falling into the Genome Initiative, 2011, the White House started that Genome initiative, material genome initiative, and I reflect back and see the projects that I got from National Science Foundation proposed is just falling exactly in this category. So today my topic is computer-aided mixed design, current status and future perspectives. I also added this one. It's a revolution that you must be part of it. I really believe, the material design will change our future. And yeah, with this is the kind of presentation outline. It's a brief history of the design, mixed design, and computer development, and talk about the various methodology or methods that we have been developing or that must be used for the material by design. And we will talk about various kind of like grading stages like digital specimen and digital testing stage and digital mix design. We got actually these two. The titles are the projects that I had from the National Science Foundation in there, and the computer added mix design or computer-based mix design perspectives. Last slide, I would ask you to make your own judgment as to whether this is something that realistically be achievable or not. So let's briefly talk about the history of kind of as for the mixed design. This one is focused on as for the concrete, but the ceramic concrete very similarly, just a different type of materials in there. But the framework might be very similar in there. We have this various methodology. Most of you are very familiar with them. And the major issue for this two actually for this mixed design have two steps. Right? One is forming the shapes or the forming a sample specimen. Another is evaluate some of the mechanical properties like stability or strength of this material. And using this example, like super mixed design is consistent of few steps over here, like say aggregate selection and as for the binder selection, compacted samples and different as for binder content and test the samples for mechanical performance and determine volumetric in there. Which before during the lunch, Imai, El and Hussein, we are talking about it as a volumetric thing in there. Although pretty fundamental, sometimes still cause problems in there. And the select, optimal as for the binder content. That's the kind of process of the mixed design. Okay, that's one. If we use the computer to do this, then our computer system or software hardware system should be able to simulate this entire process, material selection process and compaction process as well, and modeling the material behavior. Okay. There are some people from China. They're also doing some mixed design, the locking in there, and I put one stop in there. It's the national effort, international effort. A lot of work doing in this group over here. I didn't cite all of them, and just for convenience, it's the best some of the work that we did in there in my group. Computer design. I strongly believe when I hear the two persons are familiar with this type of computer. I think is Imai and me most likely, right? Okay. The bigger computers, ENIAC, it's so large, but the computing power is very minimum compared to these devices. And the time that we went to college is actually this is TQ16 or whatever. That's PDP like 8. This one, right? It's the time that we went to college that we have this type of computer in there. It's just reading the holes. You punch the holes, and then that the laser system read that one. I believe you went to college computer in that stage, right? And then floppy disk very floppy 4K whatever. It's very small. And the believe like Bill Gates in very beginning he just says 64K would be good enough. That's his own prediction. But today 46K is nothing. You cannot do anything almost. And then there's fourth generation. Most of you are very familiar with fourth generation one. But the fifth generation in the future, maybe an intelligent ones that can read your minds and be sensing together, has some kind of human intelligence in there. Potentially, we don't know what's the fifth generation, but understanding like Stanford University, there are a lot of group people that are working on this one. Silicon Valley people working on the fifth generation. Hopefully that's kind of human incorporate some kind of human intelligence in there. This is a material genome project initiated 2011. The major purpose is to help business discover, develop, and deploy new materials twice as fast. Launch this so-called material genome. The major kind of philosophy, this one is the experimental work that we've been performing all sorts of experimental, for material design. And another one is not conventional use, it's computer, modeling and simulation. And then another one is digital data analysis. We have to analyze the data to make sure we interpret the data correctly for the purpose of design a good material. And then, United States, we have several kind of genome-related initiatives, and it's list one. And the Northwestern University under the Department of Energy, they formed this kind of material by design, in there. As I mentioned, there's 3 columns, right, to support the material genome, MGI, one. And originally, they don't cover civil engineering materials. I'm championing for this one, to incorporate this, civil engineering materials. I talked to, James, Warren and NIST, and he's the technical director for the genome, at NIST. And I try to convince him this material, civil engineering material, that including the asphalt concrete, cement concrete, and the soil, has large quantity and a very big impact economically, and also very big impact on environmental issues. We have to mine a lot of the aggregates and cost a lot of resources, energy resources, and sometimes destructive to the natural environmental as well. Okay, so this one. So also China also has some kind of initiatives on genome. They put like a 500 million, for supporting the material genome in Shanghai as well. And the national efforts, they put like a 260 billion Chinese yuan to support that one. I also talked to the leaders over there to see whether we can incorporate us. But again, originally they never included any civil engineering materials. And the leader, Professor Wang Haizhou, and he just promised me to incorporate us very little in terms of the framework. And I told them that, even we don't care about the funding, but we care you have to incorporate civil engineering materials, because that's a big chunk of kind of materials that we should take care of as well. And this one actually, we got this concept, the genome IC 2012. I had my sabbatical in there in Beijing, and then I proposed to the Chinese Natural Science Foundation to have this project as a genome for gravels and a sense evolution. It tried to use this integrated experimental method, modeling and simulation, and data analysis to understand how this aggregates evolved into sands and finally into this fine sands and soils, right? Natural process and burst crusher process in there. So why certain type of mineral when it's crushed is in this type of angularity, texture, and shapes, right? And try to interpret it is use this genome approach in there. And I define that one into this composition, material defects, and kind of like a material structure, material composition, and material defects in there. And I define the material genome would be the controlling factors in these 3 categories in there. Now let's just very briefly, review the computer, design for structures. Nowadays, almost every structure is designed to use computer. Without a computer, you cannot design anything almost, right? Pavement also, we have this, MEPDG design is mainly based on computer. Although it may, incorporate on this, visco elasticity or sometimes the multi-layer theory only. But for material design, it's not the case. Yeah, we don't know, which one can be, used just use, computer to design the material. Some of the composite material can be designed. Some of the medical, materials, they use, some molecular dynamics and some complicated quantum mechanics calculations, and to design whether this medicine would interact with human being in this way or that way. But again, for our materials, we haven't reached that stage. Using computer to screen the mixes, so to make sure that this mix is not good, for this purpose. That mix is good for that purpose, all right? We have to use computer, but at this stage is not. But the pavement materials is not, kind of pavement material design is not good, at this stage. Structure design is okay. Like we have the Kappa, like Tom Scabbers, Professor Scabbers has that software as well, right? A number of software can be well utilized for the pavement structure design, but not for the material design. So
based on my understanding, there are composition, structure, and defects interactions. Right? Those are the important components of the so-called genome, concept or the genome type of, research. So we have to understand this very well, so we can use computer to screening the composition. What type of composition you should add to the mixture, so we are going to achieve this type of material properties. So it's a kind of target-driven, driven by like this is the performance I want, and this is the composition that or structure, this material selection that I would be able to satisfy your target, performance target in there. First, we have to understand this is quite a few of these numbers in there is the material structure or multi-scale structure from like a nanoscale, right, atomic scale, molecular scale to the grain or particle scale. Right? So we needed to have a kind of number of methodology, both testing and characterization wise, to quantify this parameters. These parameters can be named the genome, right, or the genes of the materials. But we should be able to characterize this. And the laboratory that I established at Virginia Tech, like include atomic force microscope, micro CT, and some image systems. Actually, this one acquired together, 34, L and me, laser wide. We had an SHP project together, and this, first, kind of city that I purchased, in Louisiana, and it's a high-end, micro city and a nano city, and this, tools can quantify or characterize, the material structure at a nanoscale, like from nanometer, right? Like in this case, this one is 0.1 nanometer, right? It could be pretty accurate, in there. So the material structure can be characterized. That's one tool, one set of tool in there. The other, material kind of like a characterization tools like a focused ion beam to cut the specimen, very tiny specimen. Sometimes you cannot use the saw to cut it, right? You have to use some of this, more advanced tools like this focused ion beam to cut the specimen in there. And like a environmental scanning electron microscope. This is actually the work that is my former, PhD student, Dr. Yang Lu did his, PhD dissertation work. Most of the work is actually my students did the work, right? And but the projects, the ideas came, and so it's hard to separate, right? But the hard working and the constructive work is important. And this is the environmental scanning. We can determine what the elements are on the surface of this material, right? And this is a transmission electron microscope. With this project, we actually identified some kind of like interface between asphalt binder and aggregates. And this actually, you see this aggregates, on this, screen, you will be able to see some kind of grades in there. But in here is amorphous in there. This is kind of like a crystal structure can be seen from the DEM. And you will see some of the smear region between this, crystal structure and amorphous material. That means there's some kind of a boundary interface between the asphalt binder and aggregates. And that's roughly 5 nanometers. That's what we measure from this project in there. So in a sense, this tools already, experimental tools, we have that already. As a matter of fact, we didn't use that, so often, especially in our materials area, we sometimes were driven by the macro scale. We did a lot, but in the micro scale, nano scale, this we didn't, work, into that area a lot. But it is there. The tools are there, and some of us will already use these tools to characterize, the material microstructure at a nano scale or across different scales. The next one, let's talk about the modeling tools. Remember the 3, columns, right? 3, so each column, let's look into, what are the current situation, whether we can achieve achieve the objectives, for the future. Now, first, let's talk about the continuum approaches. This one of them is taking into the material structure. This is X-ray tomography imaging system, and reconstruct the 3D, structure, and use the continuum or the finite element approach. But in this case, we separated 3 different, constituents or elements, like the aggregates, may be modeled as, elastical material, and the asphalt binder, the viscoelastic or viscoplastic material, and the voids, have low resistance sometimes. So we have to remove that one, consider as a cracking or whatever, right? And then this reconstruction is like individual particles. Later on I will talk about this one as well. The individual particles be used if you can reconstruct a three-dimensional representation of individual particles, and then can use these particles in the modeling of discrete element approach in there. And the first set, if you have the structure, then you may use some kind of parameters like a damage surface area, damage tensor, the spacing among the voids, or this type of geometry, or in a sense structure, to represent the material structure in terms of statistical kind of approach, right? And to link this type of parameters, in a sense, some of the defects parameters in there to the material performance. So that's one stage we can achieve. We develop various methodology, to quantify these parameters in there, and use these parameters as some kind of potential genes of material behavior. Okay. And then like this one, we incorporate this, 3D, simulation. Now incorporate, 3D three-phase material, simulation using like the discrete, using the indirect, tensor tests. Right? And use this, methodology. We actually successfully ranked, the mixes performance of the West Track, project. The West Track project has, three, mixes, the fine mix, fine plus mix, and the coarse mix. And the test results showing that, the kind of performance is contradictory to the understanding. But they use this, image analysis. When you take into the structure of the material structure in there, we successfully ranked, the performance of these three mixes. And this is actually the first project, and after I graduated, when the time I was still working with law engineering, a company, and Sashida, Naga Sashida, at that time he was working, at a federal higher administration, and he sent the images. I wanted me to do some analysis for them for free, of course, doing the volunteers. Again, volunteers sometimes are important. Give you opportunities. That time is a volunteer. But later on, and I feel this is an important area. So I started, writing a proposal to get that, first the CT, the bigger one at Louisiana State University, and then establish my career in this area. So don't kind of today, volunteering work is, as long as you judgment, this is the important thing. Volunteering work is important as well. Right? And some Chinese, community, they're also doing some work in this area. And other people like in this, in this area, like I say, some of the Chinese and especially Yamasada did a lot of work on this one. Yongrak and Kim, it's just we cannot list all of them. There are so many people working in this area, taking into the material structure into the modeling and assimilation. And I named that one. The overall is a digital specimen, digital testing, right? Using computer to generate the specimen and store that specimen into the computer. Okay, that's another project that is a unified approach for multiscale characterization modeling and simulation of stone-based materials. And in this one, we treat asphalt concrete, cement concrete, and soil as stone-based materials, and take the microstructure of this material into the consideration, and it's come up with a general framework, and that framework would be applicable to each of these materials. The only difference is changing in the kind of constituent model of the binding material, like cement paste and asphalt binder, right? That's the only difference in there. And in this project, we look into the interface between aggregates and asphalt binder using MD, molecular dynamics, application, simulation. Other areas like people doing this, like Professor Zhu, Tongji University, using the boundary element, approach. And we have other colleagues like Beyond Bergson, also did a lot of work on the boundary element applications. There are some advantages in there. It's saving, computational, kind of time, and at the same time can understanding the inner behavior and the boundary behavior, right? So it's a boundary element approach. But if we don't have a kind of unique, because this approach is different from like the finite element approach, and each of them you have to derive some kind of like a explicit, relationship between the internal, integral versus the surface integral. So it's a much complicated. It requires a lot of mathematics, and we don't have a good, professional software that can address these problems, in there. But I guess this is an important area in the future. Takes time, but we move towards the goal, the common goal that, Professor Imad Akkadi is sitting for us. For a lot of this community, it's just an academy of science and engineering for pavement. You should feel proud of that, and should tell your colleagues or other people that our materials are very complicated because it's making use of this wasted materials, right? And it's large quantity, and the service, environmental is much more complicated, like a service, condition like this one. Stay in the room or in your pocket, but our materials just put in the roads, subjected to very severe environmental conditions, unpredictable kind of traffic, random traffic loading in there. Right? So very complicated materials. Scientifically, it's also very complicated problems in there. Right? If structural people tell you, say, oh, your pavement guy is not scientific, you tell them your structural elements is much simpler than our materials. That element, analysis is a lot of simple. We learn this from college, right? But today, for this material, it's not a really challenging material. So all of you feel proud of it. You're working on a very, scientific, kind of workable problems in there. Okay? And this is a work that she did. I think it's a very nice work, incorporated viscoelasticity as well. But again, this area, I really believe there is tremendous of space for there to improve. Okay, this is the modeling in the continuum. And let's look at the modeling, in the discrete, approach, right? To say, whether this area we have a lot of work done, or we have achieved certain degrees of success or not. And the last, slide, I will ask you to make a judgment whether mixed design by computer would be feasible or not, right? Okay, this one. So this is the work that my first PhD student did. Is just from the X-ray tomography image, reconstruct the individual particles. Looks like easier, but it's a very challenging job because the computer doesn't know this cross-section, this cross-section belong to the same particle. You have to use some kind of pattern recognition approach. Like in this case, the morphological pattern, recognition approach, and identify these particle sections and reconstruct it into individual particles. The purpose of doing this one is we can evaluate some particle properties and later on represent this one individual particle in the particle mechanics. Right? That's the purpose of doing this. And you can see this one, the different particles are represented into this 3D one individual ellipsoids. Current DEM approach that using spheres, or sometimes you cluster them together, but when you cluster them, if you want to represent the particle shape, you have to use a very large number of spherical particles in there. And the computational efficiency would be much lower. And we developed this methodology, and it's with Jin Yong Park. You still remember him? Together, when he was working as a postdoc of mine at Louisiana State University. You can see this is actual particle and this is ellipsoids. But once you have the ellipsoids, although it only one more degree of freedom, but the variety of the particle shapes that can be represented would be huge. Can you see this one, right? This complicated particle, but this particle is very similar to this one. And the criteria we use is the mass must be equal, and the mass momentum must be equal. And sometimes you have to adjust the density of the particles inside of the particles in there. And the DEM approach, the ME approach, is mainly just the particle mechanics, right? And the molecular dynamics, especially the traditional ones, don't consider the bond breakage and interactions of particles in terms of chemical interaction. Then they are the same. DEM approach and the FEM approach, the molecular dynamics are the same. Only difference is here is the interaction. Right? The interaction is just the contact models for DEM, and here we use the potential. Right? The various potentials, considering various kind of degrees of freedom. And when you have like a very large number of degrees of freedom, all the degrees of freedom considered, you go to the quantum mechanics. If you reduce that one to kind of a simple interaction, then it becomes molecular dynamics in there. And we model actually the aspect of rinsing and melting, right? And in this area, that's the most challenging part, honestly, because you have so many molecules, so many types of molecules. The strings of the carbon strings, could be very long, could be different, formats, and it's hard. And we use this average molecules methodology, based on the composition and the percentage of the carbon atoms or whatever, right? Then we come up with this type of representation. And the quartz, like the aggregate stone, is relatively easy. You can treat that one as the kind of crystal material for some of the rocks, and that's why you'll see the first time we choose that aggregates. It's kind of igneous rocks because it has a good crystal structure. So we can use that crystal structure for our modeling, for validation and verification. And for some of the stones like a mother stone or some of this kind of like a kind of how say it, the non igneous rocks, and sometimes the structure is more complicated, right? It's harder to model for that one. And we model this one, the interface between aspect binder and aggregates. If you have a molecule, a water molecule, so suppose that you have a water molecule diffused into the interface between aspect binder and aggregates, what is the consequence? And we find out if you have the molecules interface in there, depend on different type of aggregates and aspect binder, that bond energy would change a lot. And some of them have a bigger change. That means this material might be very sensitive to moisture damage. And we use this criteria to rank the aggregates, that it can be susceptible to the moisture damage. And that ranking is very similar to the ranking that Bob Letting, Professor Bob Letting had that one. During one of the ETG meeting, we showed the results to him. At the very beginning, I don't understand why that's the case. And then compare with the experimental results. It shows us like this fundamental research sometimes really can be used for guiding for the material selection. Right. Okay, so that's another one. At the nano scale, we had a project. It's called a nanomechanics of structural materials. Jeff, like another project that we did for concrete. This is the one that for concrete materials. It's the modeling and simulation of cement hydration process. Cement hydration, and then forming this cement past forming the cement concrete in there. And my colleague actually Bill Goddard, Professor Goddard in Caltech, he developed this so-called Rex force field theory, just simplified quantum mechanics in a sense, but it maintained a pretty high accuracy of this quantum mechanics approach at a very high efficiency. Typically for this quantum mechanics, all computation, consider all the degrees, it can only address like a few hundred atoms. But they use this approach that they developed, they can handle like millions of atoms in there. Okay, so in a sense, from this, kind of understanding, we already have a lot of tools. These tools are kind of being used, although may not be so matured, but they have been used and tried. To a certain degree, some of them are successful, like this, aspect binder. Some of them still not so mature. But again, this is the current status, and I want you to make a judgment, in the later stages to see whether they can be used for other purpose. And this is the one, the multiscale modeling of and bridging scale methodology. Try to integrate it from this nanoscale to micro scale to the continuum, to bridge them using the concurrent approach to model the material behavior. And this is the project, is a kind of exploratory research. And this one, of course, we cannot, use this, kind of scope of funding to solve this problem. But they try to look into whether this is a feasibility, is feasible or not. Right? As a matter of fact, in 2009, the Department of Defense, they put like $89 million for the similar concept, is using computer to design some of this, 4 types of composite metals. They try to design the metals so the metals would have very high strength, 10 times of the strength of existing metals, right? And 10 times stiffer. We wrote a proposal. We tried to write a proposal with some of the material science people, and finally we didn't get that one. Johns Hopkins University, they got that one. So $89 million for design 4 metal materials. like this concrete, the multiscale is natural, right? So naturally they have, multiscale, elements in there. So modeling wise, the different scale, the interaction, mechanism be different, like forces will be different. Like the atomic force, like you have the electric charges and then strong forces in there. And some of them, there's a van der Waals forces and at the continuum level, you still maybe have some kind of surface forces in there. Right? So the forces are different, and then corresponding the different scales, the governing equations might be different. You have to consider the multi-scale interactions in there. And this is the one that Bill they developed on this one. The major issue is just bridges the scale, like from quantum to MD, MD to the continuum or the particle level, because MD is pretty matured in a sense. And quantum mechanics is also pretty matured in there. Continuum mechanics also. The only thing that we needed to focus is the bridge scale, techniques in there. And in the past, roughly 20 years, a lot of people, like Northwestern University, and then other universities, a lot of people focus on, some of the faculty members in your department also working on this area, the multi-scale modeling, especially bridge scale method. You also develop a lot of methods, by the different researchers like this, causal continuum method, coarse grain, molecular dynamics, atomic, finite element method, and this, hand shaking method, and various methods in there. This, we are not going to focus on to discuss about the details of this approaches, but the magic concept over here is just equivalence. Okay, so from this scale to another scale, we cannot maintain all the detail that will be continued, right? It be continuous. I can say, particle to particle is each of them. If it's continuous, then you reduce to the finest scale. Then computation efficiency would be very small, right? So the so-called bridge scaling methodologies maintain certain degree of continuity, like very similar to our finite element method. You may not be able to require like force and displacement are exactly the same, but it requires the multiplication of them are the same, or the energy is the same, right? Many of them just follow this type of rules, like energy is equivalent. And also like time-wise, how we can average it. Like there are some kind of like principles, like I said, talking the time domain average versus the space domain average, how they could be equal to each other. That's as a nanomechanics, we have some principles in there, assume that they are the same, or they prove they are the same in there. We use this type of tools, like here are some of the basic methodology, the tools, this different methods in there. I'm not going to go to the details in there, and various methods. And one of them is like a combined MD and a DEM approach. As I mentioned, to you, like the DEM and the MD actually they follow the same governing equation. All this, the procedure is the same. Right? The only difference is the interaction difference in there. And use that one, you can integrate this one, to represent the particle interactions or the atom, the molecules interactions, and direct into this particle interactions. And use this approach. Professor Bjorn Bergson actually did some work on this one as well. It's a lot of it's just not one person. There are a lot of people working on this one. Sooner or later, I think we will be able to, have some kind of breakthroughs in there. And this is the approach that we adopted. Is this, kind of starting with finite element simulation and determine whether there is a kind of a singularity in there, or some of the region maybe subject to a very high strain rate, or some high temperature, or some very large stress concentration, and that region we consider as a kind of like singularity region, right? And if you have that singularity region, then you need to incorporate some more detail of the material structure, like involve like a MD simulation, and the MD simulation and the FEM simulation, they are passing the information, at the shaking, the handle shaking region in there, and then that's this loop. So integrated this MD simulation into this FEM simulation in there. Shaking handle region. This is just the general philosophy. Actually, we did this one with some simple examples, and then some of the region we indeed incorporated this MD in there, and the molecular structures in there. Then you will see the stress distribution would be significantly different in there. And some analytical approach like dynamic mechanics, you consider the arrangement of this particles or molecules and derive some kind of especially for the crystal structure, it's possible to derive some kind of analytical relationship between the particle level forces versus the continuous type of forces in there, right? So direct transition from this, particle level to the continuous level, possibly. And another approach, we also tried is called a fast field application. It's just using the fast field methodology and using the MD simulation to calculate, the free energy. And from this free energy and the variables like displacement, rate of displacement, and the derivation will give you some kind of constituent models in there. And this approach at the very beginning is for the actual application, the simple application, but later on I find that this is actually a good bridge scaling methodology from molecular dynamics to the continuum approach. So in a sense, this slides just tell us this methodology, from experimental method to the modeling simulation method, we have a lot of research activities going on. Some of them successful, some of them still in kind of like a trial and error to see whether these models are fitting for the application or not. Right? The next one, remember the important one is just the methodology. It's just a data analysis. The data, I think we should have. Oh yeah, we still have a lot of slides. You have to go quickly. Okay. Data analysis. Next one, I think first what we need. I always say what we need and where we are right now. Actually, we need like a composition structure of components and the properties, binder aggregates, additives, and mixtures in there. Mixed design data, right? Gradation aspect, volumetrics, mixture properties, physical, mechanical, and chemical properties. Performance data, distresses, and environmental loading in there. We need all this data in there. But the challenging thing over here is like we have this actual road test, LTPP, SHARP, WestTrack, many of these tests in there. The completeness of this data. Sometimes we have this set of data, but we don't have another set of data. And consistency. Some of the data collection, is not consistent, right? And then, variety. Some of the data we just have on this piece of data. We don't have another piece of data in there. Volume, all these things kind of not available, or completeness is a bigger challenge over there. So one of the kind of challenges is, some of this is a cause and effect we still don't quite understand. We based on the mechanical analysis, stress would cause strain or whatever. But that kind of assumption for some of this, phenomena may not be valid. Right? So the cause and effect will not that kind of like thoroughly understood in there. And then why not correlated? Well, some of them correlation is good, some is not, right? And how about new material designs? Right? New material designs, you don't have something to guide you through. You have to use this, fundamental rules and principles in there, and a solution that, maybe applicability of bigger data analysis in one thing. Coordinated efforts, it's very important. And when we do the research, we have to coordinate the data that we collected. Types of data collection procedure must be formalized every, following in very similar format, so we can make use of the data in there. Now, data sharing and intellectual properties, reliabilities, as you presented the data, whether this data is true or accurate or not. How to analyze incomplete, inconsistent, small or bigger data sets. That's a very important thing, in here. That's our LTPP data, competition, right? So many years, it's still having problems in there because that's incomplete, inconsistent. Sometimes bigger data, sometimes small data. So all these things, in there. So the next step, this is a kind of fundamental, kind of research, area. Next step, we talk about like digital specimen, digital testing methodology. This is a National Science Foundation project. Try to develop some kind of modeling approach for the material behavior using the material microstructure. We call that one the microstructure, kind of complete representation as a digital specimen. And the modeling the overall evolution of the microstructure is called a digital specimen method. Right? We applied a viscoelasticity model And we also did this in kind of simulation is just using a micro CT, right? Micro CT to look into the structural interactions. You can see this, dilute and some kind of like a also diluted, and this one is forming the particle, skeleton. When the material reach like aggregate reach 50% in there, and we turn this material structure into the mesh and modeling the material behavior. Yes, this one. Modeling the material behavior, and this is also one I just added in there. Is a macroscopic modeling. This Hussein mentioned compaction. We did this work. The macroscopic. Later on, we will the DEM approach. We'll talk about the compaction of the DEM approach in there. And then this one, extended one to the binder, and you see the wax distribution, and this wax would affect the binder properties as well. And using similar approach, you can modeling the behavior or the material performance if you contain the different type of wax contents in there. Particle, approach, reconstruction, recognition. We did this, digital specimen along this, DEM approach. This is the direct shear, methodology, and we reconstructed individual particles and represented them into, this, cluster of particles in there. And using DEM with this digital specimen, digital testing methodology again, two categories. One is following the FEM approach, and another is following the discrete element approach. And the model the direct tension test. Why this? Cannot see anything over here. It's there. I don't understand. And measure two things over there. The cluster one. See this experimental measurement, and this is a cluster DEM approach, considering the particle shapes in there. And these patterns are very close. But unfortunately, I don't understand why. Why today this is not there. And this kind of conventional approach, you will see the kind of movements is scattered everywhere. And that means not consistent with experimental measurements in there. And correspondingly, the rotation, the particle rotation, is also not consistent if you use the conventional DEM approach. You can see this random kind of movements, but for the experimental, it's showing some kind of pattern, and also the strain localization in there. And use the simulation by the clustering DEM approach, you can achieve this objective. So compaction, we also use this compaction DEM modeling, incorporate a different type of aggregate shape in there. Look into different aggregate shape, how the aggregate shapes affect the compaction effects. Others, there are a lot of people working on this DEM approach, and your colleague Bill Bartner, Professor Bartner, and his student Yu, and quite a few of them colleagues, they're also working on this DEM approach for modeling the material behavior. The major challenges in complex shape should be considered. Right? And the digital mix design, that's another one that we're doing this one, is try using the original ones, like we talk about the digital specimen and the digital testing. And this approach actually we reconstructed the 3D structure from X-ray tomography imaging. But how about we use the computer to generate the material structure, right? Particle generated in this particle structure in there, or use the existing structure, particle shapes, like the ones like developed by Ed Gabalzi, right? They actually scanned the 3D representations of 50,000 particles. And now probably it's more than that. Last time he told me like maybe 60 or some thousand particles. And how would they use this computer, this existing particle, and they use the computer to random pack them together, right? To form a structure that is kind of like a gradation design. That's right. That's what we do. Actually, we use the computer to generate this kind of closed packing, really closed packing structure for the gradation, and the best one to select a gradation in there. But we cannot rely on the closed one. Right? Some of the particles, when it's close to this, the highest density, then you have some kind of stability problem. Easy to lose stability in there. And use this, computational methodology to mimic, to simulate the compression test. And then in this case, can reach, kind of different strain rate, reach the peak stress. and using different aspect binding content in there. We just use the computer to generate the aspect binding content in there, and determine that some kind of like aspect content is roughly some kind of 5 to 6%, 5, 3 or 4%, of aspect binding content that will be reaching the maximum strength in there. So it's in a sense, mimic our compaction process in there. Different shape effects, cubical particles, right? Rod and hexagonal discus blade. And you see this in different ones, and the indirect tensile stress will be different. And these cubical particles will give you larger, kind of tensile stress in there. And it's reasonable because the cubical particles are sometimes more stable in that sense. The movements. This is using DEM approach, discrete element modeling. This is kind of different shapes, and we use this one, the X-ray tomography image, using the DEM to model this, kind of specimen performance. At the same time, we're scanning this, scan the specimen and to see how the particle moves. And that's what another. I think the project, the project is over, and soon we're going to have another paper coming out of this one. Okay, and the density, compaction, temperature. How about the temperature? Different temperatures, what could be the density that can be achieved? And also use the kind of like the DEM approach, the discrete element approach, and to model the compaction process in there, determine what would be the optimal temperature for aspect binder in there. Okay, so that's kind of like a overall kind of review of what we have done so far. It's just limited, not just citing all the work that other people have done, and the majority of the work that we cite over here is the work that we've done in my group. And there are a lot of people make a lot of contributions in there, and for time, kind of limitation, I didn't have the time to solicit, the slides from them. Some of them I got some slides from them, but some of them didn't. Right? And let's see this kind of more advanced tools, characterization, and modeling approach. Maybe we have to focus on this one as well. And one important thing is database. Really, we don't have the historical data. And the data that I did with my group typically is there. We didn't systematically, manage this data. Active researchers. We need to have active researchers and coordinate them together, both national and international, efforts in there, and industry support. Finally, we have to convince the industry. Yeah, this is something promising. You have to invest, and then we can develop some kind of a material studio for our materials. Remember, the material studio for metal materials, for other materials are there, but they're not for us, right? So we may be able to develop a so-called civil engineering material studio, right? And can be used for this purpose. And my prediction over here, and I believe partial replacement, or in a sense, not all aided, computer aided mixed design. Within the 10 to 20 years, maybe we will be able to come up with some kind of code. This code can be used for the material design, and the direct applications maybe 30 years or after. 30 years, it's reasonable because a tool that can be used for direct kind of mixed design must be verified and validated, right? And you have to gain comfortableness in using these tools for doing at least quite a few mixed design and make sure they are working properly. Then at that stage, you will be able to use these tools. Okay. Two announcements, right? So one is the Transportation Research Congress, and our colleagues over here, Professor Imad Akadi, he's the only one serving on the advisory committee here, advisory committee chair, co-chair, and me, the executive committee, and Have Fun is also here, Jenny, and Ouyang, Professor Ouyang would be in charge of this traffic planning area as well, and Professor L. Childrenman will be invited for keynote speech for the subgrade geotechnics in this area. Professor Akadi would be also a keynote speaker for the pavement and the materials area as well. And welcome everyone to go this one. It would be interesting one. And then another one is actually international workshop on genome of civil infrastructure materials. And that will be the end of this conference starting on June 8th. And we have a number of researchers in this area. Quite a few of you will be also attending this one and give invited talks. Like Professor Imad Akadi will be also giving a talk in this one. Because this different angles. It's not only just modeling, it's overall integration, right? It's how to form kind of like consortium in the future to work together to come up with something that is meaningful and helpful. And this is one. And that's some of the Chinese students if you have over here, and then just also send the messages to them. We are building that national center, and then we'll be having as for the laboratory, and we have two accelerated pavement testing devices. One is environmental controlled, environmental controlled one, and another one is non-environmental controlled, is a testing track area. And as for the laboratory, it's in here. So with that, I would like to thank all my students and the funding agencies as they hard work, innovative work, and make this happen. And I believe sooner or later, Arrow and everyone maybe just claim in the future, you students here also make a lot of contributions. This is a top program in the world, and the students here are very smart, and I believe if you working on this one, you will make more contributions and better contributions as well. Thank you very much. And that is.
Questions for Professor Wang?
It's an excellent presentation. I really enjoyed it. You mentioned about in your last slide some applications, direct applications of such in advanced modeling characterization efforts. So how do you foresee an application of multi-scale modeling, for example, in payment design? Are there any goals that you have in your roadmap, intermediary, long-term, medium-term applications that we can use such techniques?
Yeah, that's an excellent question. Remember, in the TRB, there is a subcommittee. It's called the integration of material design into payment structure design. Ray Rookie, Professor Ray Rookie is kind of leading that one. But later on, I didn't see a lot of progress in that. My understanding is this: the payment, we may be studying the existing payment designs, and later on, you have this interaction, material design and payment structure design together, interacting with each other. If you were starting with this current design methodology, at least we have to accommodate the current pavement design. Later on, then we improve it. Right? The current one, that will be pavement structure analysis, viscoelasticity, or some of viscoplasticity is a continual approach. Right? It's a continual approach, and then go to further step, down from the top scale to the down scale, right? And you have incorporate like the particle level, aggregate shape, angularity, and texture, right? That's some of these parameters that we use for our mixed designs today, right? And that's one level, kind of interaction in there. So in this one will be used to guide the selection of aggregates, right? And the type of aggregates, like the shape, angularity, texture, and the interface between aspect binder and aggregates. This can be accommodated. This is particle mechanics level, right? And then further step down, like say, we are interested in recycling. We add mixtures in there, and we add some kind of additives in there. But what happens if these additives are added to the aspect binder? What are the consequences in there? Then we can use this kind of quantum mechanics approach to predict it. If I'm adding in this one, then this causes this type of consequences, right? And this to guide us to select the mix, mixtures in there. But once this is done, then we have to, experimental approach is still there. Then we have to, using first computer, methodology to come up with a kind of draft mix design, and then using experimental methodology to validate and verify this one. Okay. So this is integrated together: experimental, modeling and simulation, and the data analysis. So that's my understanding. So this is the way, from the very beginning, from top to the bottom. But in the future, when this becomes very mature, everything is so good, and you don't care about whether it's bottom up or
top down, right? The top down continue to the quantum mechanics. And later on, you say, oh, I'm getting this one, I'm doing the quantum mechanics modeling first. And then you are just kind of like a direct methodology from mixed design to the structure design. I'm not sure whether I can.
Yeah. I was also wondering, are there, like, since you are now also chairing the civil infrastructure effort in NSF or such multi-scaling modeling effort, are there other infrastructure materials that are considered to be more critical than payments? Like currently using such, for example, advanced techniques in designing their structures.
Yes. Yes, actually, that's the Genamo initiative, 2011, and the corresponding the NSF Porter material design. It's a DEM whatever. I don't remember that. Exactly. That's the initiative material design. And this last call is January 19. I didn't have time to do the job. I didn't have time to put a proposal in there. They focus on metal materials, right? Metal and some kind of polymer materials and composite materials. And I sent an email to the program manager and to say whether the civil engineering materials could be considered in that. And she told me yes. And but unfortunately, due to the TRB and almost the proposal is ready, but I don't think that'll be kind of fine-tuned enough. So I didn't submit it, but later on maybe submit a proposal for that one. Other materials they have, especially metal materials. They use this kind of Genamo approach for design the mechanical materials in there.
Well, yeah, go ahead. I have a question.
So my question is, when you are modeling different kind of materials, like for example, binder or asphalt mixture, like what kind of properties are you actually pick up? Like how do you characterize? Because there are infinite number of there are so many number of properties which we can use to define a material. Right?
Yeah.
So how do you select, or what properties would you select to characterize a material? Like?
Yeah, I think that's a very good question too. Different level, different scales. When we talk this one, it's part of different scales. But if we talk about it like a nanoscale or quantum mechanics level, the things is just composition, and the atoms, the molecular structure of this material, and some of the measurement of the potentials of the interaction of different atoms. That's the fundamental kind of inputs for the computational simulation. Right? That's one level. And another level, maybe going to above, that's on particle level. Right? Particle level, we use this, general particle mechanics or the discrete element approach. And this approach, then you require the particle shape being incorporated, and this, particle, kind of center, coordinates. Right? This, be required. So that are and also the interactions, the contact, behavior. Between the particles. Okay. And the continuum level, that's then you depend on whether it's elasticity, viscoelasticity, or viscoplasticity. You have this parameters in there, and these parameters sometimes can be calculated from the lower level computational simulations as well.
Well, just to follow up on that, I have two quick questions. I was catching things as you were presenting.
Don't change me too.
But just like what you were mentioning about, the different scales, multi-scale, right? Yeah. In some work that we did originally, looking at some individual grains of, for example, aggregates, we're capturing aggregate shapes, and we're very good at that right now, right? Angularity, the flatness, elongation, the shape, and everything. When you go down to the molecular level to look at some, from a geology perspective, like thin sections and things, the individual mineral grains, some of those have some properties, shape properties that are similar to how actually our crushed stone has been crushed because of, again, inherently they're coming from that molecular level, that atomic level, the way they crush. Well, also there's crusher's effect too, but a lot of that comes from that engineered material type, grain size and grain shape.
Yes.
So I think you showed some of those, and some work NIST is doing, Ed Garbozzi is doing.
Yes.
So have you found that this match?
Okay.
The quantum mechanics you mentioned, but molecular size versus.
Yeah. What we did is there's one thing is interesting. We studied 4 types of aggregates. Both are this, igneous, aggregates, and all of them. And we try to, remember, the green, particle, right? And then the the crystallographer, right? The dimensions, A, B, C, this type of
That's
lattice, parameters in there. And we use the MD simulation in there, and then kind of like looking into this, different type of cross section in a sense, right? And use these parameters to come up with a correlation with the accurate shape, angularity, and texture, right? And the magic one is texture, because the shape would be very much related with that, crusher, kind of forces, types of crusher in there, right? But the angularity and texture are very much related with this, crystal, kind of like dimensions in there. And with these three of them correlated very well with, the aggregate, texture. But in the other one, it's not. And we didn't publish the student, actually the former student, Dr. Sun, putting a paper together. But I'm still kind of like hesitating whether I'm going to send this one publication or not, because this one is not well correlated. But the magic reason, I think probably that's related with the potential. Not only just the dimension, the structure, but also the atomic interaction, the potential would be also one factor in there.
Yeah,
I think that's a
I think
really,
what's happening at the atomic level is affecting final shape,
yeah,
as well as there's Crusher's effect, but also if you look at the grain shape,
Yeah.
they have resemblance.
yes,
to
yes, yes.
The second question I had was, you mentioned about the importance of, again, shape, especially when doing the gradation in the computer-aided design.
Yeah.
Packing order and how
Yeah.
you're studying the gradations and things. We have been doing that recently, well, at a larger size, like railroad ballast size or
Yeah.
coarse aggregate
Yeah.
size, and using actually a three-dimensional polyhedron size or shaped actual, really,
Oh, yeah, yes, yeah.
right, irregular shaped crushed stone to be captured with the actual angularity and polyhedron shaped elements.
Yes.
But I know a lot of the DEM methods, including the ITESCAS, PFC 3D, and others that many people use, they always put together those spheres together, right?
Yes.
So you miss the angularity, you miss that friction angle represented in behavior, you miss the packing when you do that, even in the discrete element modeling, to study what kind of gradation and shape come together
Yes.
for the best arrangement, for the best mixed design with asphalt binders there.
Yeah.
So have you done differences or study differences between spherical element models with DEM versus actual 3D polyhedron shaped elements?
Oh, we didn't use polyhedron right now. We use this cluster. Remember one of the slides showing that we put a lot of small spheres
Clumping.
and clump them together to represent that complex particle shape. And within that particle, we use a larger sphere to represent a lot of small spheres, right? So the number of particles will be significantly reduced. But again, we didn't consider that one, especially during the compaction process.
Don't you think going to 3D shape, polyhedron shape is better?
I think it should be better, because that one it is it's more accurate in terms of shape, but only one particle, right? That's the biggest advantage in there. But as a DEC, that they have this kind of capability in there. Right? I didn't try that one, but later on, I believe that ellipsoid representation, it is having a good advantage. We didn't follow up. There is NG from Michigan, Mexico, New Mexico State University. He tried that one, but it only focused on very few particles. They didn't, come up with a kind of commercially available software. And,
I don't want to dominate this, but we have one for years with Professor Gabussi's work.
It was,
Professor Ashash and I, we've been working on this.
Yeah. Yeah, I think that's
it makes a huge difference. I know French people are working on it quite a bit now.
Yes,
and others, and Japanese too.
Yes.
So.
Yes. That's a good area. I still believe that is a good area. Sometimes this fundamental research is harder to sustain, and only within a bigger group, like people working together, some applied, some kind of modeling. You have one person, focus on some fundamental research, and then other people fundamental integrate together.
Is NIST computer model still spherical? The 60,000 particles Ed Carbonsi was
Is
doing?
the irregular particle shape using like 3D spherical analysis.
Oh, spherical.
But they didn't put that one into the DEM modeling, it's particle modeling. Didn't. They come up with some kind of abstraction of the morphology, properties, characteristics, but they didn't go step further, take these particles into modeling and simulation.
I have a question.
About the empirical mechanical design. So are we moving from this design in 30 years to the completely mechanical base, or still do we need that empirical aspects? For example, understanding the fatigue models better, maybe for using the computer-based designs.
I think that's a question. I guess how to say. 30 years from now, I believe still there are some kind of empiricism being incorporated in there. It cannot be completely, especially the environmental conditions cannot be completely taken into this consideration. Like equivalency-wise, for example, like the temperature changes, so big variation in there, right? How this kind of sequence, the temperature sequence, would affect our pavement performance? It may not be easy to understand, even within these 30 years in there, right? So that's something I believe still maybe requiring some kind of like a empiricism in there. But the empiricism would be significantly reduced. In the 30 years, if I convince you and especially Professor Imar Kadi and some other colleagues to put a lot of efforts in this area, right? But it's harder, Then you have a group of people sustaining doing research in this area. We may have some kind of better achievements in there, but still there are some empiricism because this environmental condition would be very tough, performance-wise, right? But the mixed design, this laboratory design, I think we can achieve that. Like using the computer to come up with almost the same mixed design as you can acquire from the experimental methodology.
Okay, maybe one last question. Yeah.
So it was a really good presentation, first of all. So I was going to ask you about the discrete element modeling. So I don't have any experience on that model, but a couple of months ago, Professor Hashash was presenting his work about discrete element modeling, and he told us there is a particle size limit where discrete element modeling works better. And he was, maybe I remember mistakenly, but he was telling us like 12 millimeter or 14 millimeter. That's why he was telling us that he mainly works on ballast, the railroad ballast rather than aggregate. But now I see your work that you are using discrete element modeling to model the aggregate that's used in asphalt concrete. So I was wondering if there is any size limit where discrete element models working better or not working well.
No, I think indeed the models depend on the interaction. Right? Particle size is not a critical issue. It's the particle kind of like an interaction model that you put in there that make a difference. For example, when the particle become very, very small, the surface forces become dominating. And our current methodology, like the DEM version, is consider only the body force as interaction in there. But so when the particle size become very, very small, fine particle, even like clear particles, you have to put the surface charge, the van der Waals forces, all these things, and then go to the molecular dynamics. You agree with that? So it's kind of together. This is sense the interaction, and you consider that interaction, it becomes molecular dynamics. Okay. Did I answer your question? Since the particle size is
You meant actually the number of particles, not the size.
Yeah.
or the number of particles,
Right?
the particle size. I think you are interested in the particle size.
Well, I think you're coming from just to solve a realistic engineering problem, how many particles you can handle from a computational speed perspective.
No, I do remember that he was talking about particle size. He was talking that the now the way that he's using it. Maybe I remember wrongly, but
I understand your question. As I mentioned, there are a group of people in soil mechanics. They are using the DEM approach in modeling the clear And the clear behavior and the granular soil, they have different properties. Particle interactions are different, right? The clear level, you have that, surface charge, surface force, polarity, it be a rule in that. But this can be put into your model, the DEM model. So that time, the DEM model, you would consider this, this type of interaction. And this type of interaction might be, satisfied, maybe, described by the LJ, potential functions, right?
Okay.
Okay.
Thank you.
So, you're right, it's particle size.
All right. One more.
We have a meet and greet session.
Yeah. All right, let's give a big applause. Good job.
Thank you.
Souvenir. Keep that one.
Yeah, this one, huh? Okay. I have this electron.
Oh, you do, yeah. Good job.
Thanks.
But they study the packing by actually doing the packing. Studying the packing, we were trying to understand some of the arguments between the railroad. They make sense.
Yes.
Because they go very uniform, right?
Uniform, yes.
It's like 2 to each side. So we lose stability.
Yes, yes.
And if you go a little bit evaluated, you gain stability, and then you don't lose anything from the stability,